if we have a droplet, here and we want to know, is there any pressure difference between inside the droplet and outside the droplet? Means outside the droplet means atmospheric pressure, and inside the droplet whether pressures are same or pressures are different. If we want to give the answer to this question, then what we will have to do, we will have to develop a figure in such a manner so that those parameters start coming into figure. So, this is the way we develop the free body diagram. In this free body diagram, what we have done, we have divided a droplet into two halves. So, when we have divided or we have imagined to cut it into two halves, then what we can do, we will draw the figure for the left half of the droplet, where on the top surface, since this top surface was in contact with the right side top surface of the droplet, and this surface was exposed to, or it is still exposed to air. So, that is why these molecules are subjected to surface tension, and if surface tension is equal to sigma, then what is the force in this direction is equal to 2 pi r perimeter multiplied by surface tension sigma. This is acting in this direction, in x direction. Now, if there is a pressure difference between internal surface, inner side and outer side by quantity del P, then del P into area, projected area. What is projected area? If r is the radius of the droplet, pi r square into del P. And under steady equilibrium condition, these forces due to the pressure difference and due to the surface tension will be same under steady equilibrium condition. So, that is why we can write this equation for a droplet 2 pi r into sigma, this is due to the surface tension, is equal to pi r square into del P droplet, this is due to the pressure difference, and del P droplet may be written as Pi minus Po, internal pressure of the droplet minus peripheral or external pressure, that is known as atmospheric pressure, is equal to 2 sigma divided by r. So, with the help of this formula, we can say that there is a pressure difference for a small droplet, and if r, radius of the droplet, tends to infinity, then this will tend towards 0. It means Pi minus P naught will be reducing to 0 or will be equating, right. So, for a small droplet, there is a pressure difference, and that pressure difference is function of radius as well as surface tension. Now, we have this figure. In this figure, what we have a bubble. Bubble means it is having air inside the surface, alveoli outside the surface. So, if we have a air inside the surface, then innermost layer will also be subjected to surface tension and outermost layer will also be subjected to surface tension. Because of the contact of inner molecules and outer molecules, we have twice of surface tension force in comparison to water droplet. So, in this case, we have twice of surface tension, 2 pi r sigma s, this is the surface tension force, is equal to force due to pressure. So, del P bubble multiplied by corresponding projected area, that is pi r square. This will lead to formula del P bubble is equal to 4 sigma s divided by radius. So, in case of bubble, the pressure difference will be 4 sigma s divided by radius, right. Now, we have this third figure. In this figure, we have these two pictures. One is the, in case of water, what is this contact nature, and in case of mercury, what is the contact nature. In case of water and glass, we see this phi. This phi is less than 90 degree. This phi is less than 90 degree. When phi is less than 90 degree, in that case these type of fluids and surface contact, because surface tension is a binary property, it comes into picture. It is not only the water or fluid, it is water and it comes in contact with what kind of surface, whether it comes in contact with air, whether it comes in contact with glass, whether it comes in contact with some other material. So, if phi is less than 90 degree, then that fluid is termed as a wetting fluid. Wetting fluid means this will wet the surface, like we might have experienced in the practice that if we have a wood surface which is smoothened with the help of some external material like wax, and if we pour water over this surface, then this water does not wet this surface. And if we have a simple wood surface and if we pour water over it, then it will wet the surface. So, depending on the nature of contact between the water and the surface, and if phi is less than 90 degree, then this type of fluid will wet the surface, and if phi is greater than 90 degree, in this figure we see that phi is greater than 90 degree. If phi is greater than 90 degree, if phi is greater than 90 degree, for that interaction, in that case this type of fluid does not wet that kind of surface. Like mercury, mercury does not wet the glass, but water wet the glass. So, we have understood what is the difference between wetting fluid and non-wetting fluid. We can understand this with the help of another way, that is cohesive force and adhesive force. In case of water glass contact, if cohesive force is more, let us say if cohesive force is more than the adhesive force, in that case cohesive force means force between like molecules, and adhesive force, force between unlike molecules. So, if cohesive force is more than the adhesive force, then we have this situation, means molecules will remain cohesive to each other and they will not wet this surface. So, if cohesive force is more than the adhesive force, then this type of fluid interaction with that solid will be non-wetting, and if cohesive force is less than the adhesive force, like in this case, so in that case this type of fluid interaction with that solid will wet the surface.